Hello, my mathematicians. This is Miss Foster with one of Dr. Bowler's Mindset Mathematics rich problems called Tile-It. We're going to be exploring lots of different geometric concepts here. And one of the big challenges will be to add your visual and three-dimensional sense of how things are to the vocabulary for geometry. There are so many words to learn, and the more you learn them, the better you'll be doing. So for Tile-It, we're going to be working with a geometric concept called tiling. It's also known as tessellating if you prefer to use the fancy geometric language of the upper school. And what it means is that we've got two-dimensional shapes. Now that means that they are flat. They don't have any depth, but they go up and down and side to side. Anything that you are seeing on your screen has been turned into a geometrical shape. In fact, if you're looking at my face right now, this might be the most two-dimensional thing that we have for you to look at right now, because it's only the depth of an electron or two. Now these shapes, if they're going to tessellate or tile, must fit together without gaps. Nothing in between them. And they must also be able to do this repeatedly and infinitely on a plane. Oh, we're going for an airplane ride? No, we are not. We have this kind of plane, but that's not what we're talking about. Oh, I know, Miss Foster. We're going to do woodworking, just like your Uncle Matt, who is an Olympic woodworking champion. It's true. No, this is his tool that he calls a plane, and it is something that woodworkers have used for hundreds of years to make wooden boards plain. But no, what we're talking about when we say plane is we're talking about any two-dimensional flat surface. It's just another name for it. So you can see in this picture right over here that the floor is a plane surface and it's got tiles on it. And they took those tiles right up the wall there, didn't they? I think that the ceiling is probably flat, so I don't know if it would work, but we could even put those tiles up on top. And you can see there's maybe a little bit of stuff in between them. That's called grout. But if we didn't have grout, that's really to take care of imperfections and to help the tiles stick where they're going. And so if we didn't have grout, these tiles are two-dimensional, fitting together without gaps, repeatedly, and infinitely. Which means that if this floor went on forever and ever, we could use one kind of tiles. Now you probably have seen tiles at school, maybe you've seen them at home, in restaurants. Over here on the right, I have lots of different examples of floor tile and wall tile that I found on the internet. And you can see with this black and white one, it has special places where it lines up. It looks like maybe we're using a rectangle and a square and another square. So they've got all fitting together there. Here, these are all different colors at the bottom, aren't they? Whoops, sorry for writing on that. But they're all pretty much the same shape, and they fit together by tiling. So that's what tiling is. Now, you will be using this group of purple shapes that Dr. Bowler and her crew at UCubed have produced for you. And you are invited, as part of this math extension activity, to figure out which shapes can tile on their own and which can't. Okay, so what did I mean there? Let's go back to our first page. Right here, this tile is looking pretty much like a square to me, and it looks like it just keeps going and going and going. This one down here, can you see that sort of happening? Now the perspective is funny, but that just seems to go and go and go. So all of these are the same size shape, and they tile together. So which will do that on their own? Will the equilateral triangle do it on its own? Will this septagon, 1, 2, 3, 4, 5, 6, 7-sided regular polygon, ooh, so exciting, will this tile on its own? How about this interesting irregular polygon? I don't know. I don't even know what you call this one, but I would love to play with it. Maybe I will get to this week. So some of these will tile on their own and some won't. Once you've figured out which ones will tile alone, then you could explore the next question, which is which groups of shapes can tile together? What are you talking about, Miss Foster? Well, back here on this one, I have a rectangle that is gray, and you can kind of see it there. It's got a little perspective. Then we have a square that is the height of the rectangle and is half of the rectangle and black. And then we have another square that is the same size as the black one, but is white. So here we have a rectangle tiling with a square, or two squares. We'll be getting more into this particular style of tiling later on, so get excited. So are there shapes here that we can put together and make them tile? Or not? Which ones will work together? Oh my goodness, so many possible combinations. How will you know if you get them all? If you watch that combinations video that came along with painting pieces, or if you need me to send it to you, please let me know, because that would explain the combination thing to you. What happens when shapes don't tile? Now, I've looked at this question and I imagined one of you saying, nothing, Miss Foster, we'll just know that they don't tile, and that's true. But what that question is actually asking is, what happens geometrically? What happens in terms of putting things together when they don't tile? So think about a mathematical answer to that. In real life, just playing around with these pieces, probably not the end of the world, but mathematically, what is going on there? Now, for each discovery that you make, I am asking that you turn in visual and written proof. So your visual proof needs to show me what you created and be convincing to me and anyone else who sees it, and your peers will likely see it if you turn this work in, which I hope you will. Will it convince them that the tiling will go on infinitely? So I found a tile that Dr. Bowler gave me in my book, and I just made this little model of it. Is that enough? Some of you, I bet, are shaking your heads at me. Well, then I snipped it again and got this much of it. Is that enough? I feel like I can't even know for sure what this shape is. Is that enough? That's bigger. I can see there's more than one square here. Is this one enough for you? Well, now I can see the whole shape, but I don't know. Do you need even more? See, this is a question you have to ask for yourself, but please answer it in the context of your peers in class and Miss Foster and her very old eyes. Make sure that I will be convinced too. But the picture will not be enough, my friends, and this is partly because one of Dr. Bowler's big goals for any mathematician is that you learn to share your reasoning with clarity and convincing proof. So while we want a good picture, and we'll let you decide which level of this you need to provide us in a picture, I'd also like some writing. And my writing is not just to get you to practice your reasoning, it's also to get you to use as many geometric vocabulary words as possible. We used to teach geometry first in 4th grade when I was a 4th grade teacher, and all the kids who were really good at reading and writing did really well with this unit, because they really were willing to play around with all these crazy terms down here. Then we would go into talking about addition and subtraction with regrouping, and those kids all of a sudden weren't doing as well, and the kids who struggled with the words were going gangbusters. So I'm asking you to do both, and this will be challenging. It's hard to write and talk with words that you just don't know, so I advise that you make a little game of it, or set your own little goal. For this discovery that you make, will you use 3 of these words, but will you use 4 for the next one? In this right here, I think I could definitely use the word square, although I already know that one. Octagon might be challenging. I see many regular polygons in here. What could that mean? I see them being adjacent. I see them being, there are some parallel lines going on here. And you want to know what? There's even a parallelogram in here. So finding out what those words are and then using them will help to build your geometric vocabulary. And then your upper school geometry teachers will be so happy with me, they might even bring me flowers. Hey friends, thanks for playing math with me. Have so much fun with this rich problem. And remember, you can do a tiny bit and say you're done. But the real mathematician will get curious, will start wondering, won't be satisfied with just one thing. Will really dig in deep and think and communicate deeply. Thanks for playing math with me. And until next time, bye-bye for now.